Hi, and welcome to 5.5 Incline Plane. In this worksheet, we do a lot of crazy problems where there's friction on the inclined plane. We're gonna have to break up the force due to gravity into perpendicular and parallel components. It's a bunch of steps. Now, you guys know how to do all of the individual steps, so definitely try this on your own first. Drawing the free body diagram and breaking the weight into the components, I would say, is the trickiest thing about this. But then after you draw your free body diagram, you should be able to analyze it and figure out everything else because you know how to do all the steps at that point. All right, so let's see. A 75-kilogram skier releases themselves from rest on a snowy 20-meter long hill that is inclined 30 degrees above the horizontal. Does the skier remain at rest or slide down the hill? So the skier is on this incline, and I'm just going to draw them as a box. Oops, wrong tool. Let's see. I'm just going to draw them as a box like this. And try to, as you're drawing these, you might want to use the corner of your paper to make a right angle, because sometimes when I draw it, it like comes out really wonky like that. Just try to be as neat as possible. And that's definitely not a 30-degree angle. That's more like 45, but it's okay. That's fine. We could even draw the hill. Sometimes it helps to visualize by drawing the hill just like that. And this is a 30-degree angle. And the mass of the skier is 75 kilograms. And VI is equal to 0 meters per second. G is equal to negative 9.8 meters per second squared. And the distance that they travel is 20 meters down the hill. And that's about it. So does the skier remain at rest? Oh, no. What else? Skier, snow. We could probably figure out what the coefficient of friction is. So here's where we get into like the nitty gritty. I'm going to look up in the reference table the coefficient of friction for ski on snow. Do I want to know what the static coefficient is, or do I want to know what the kinetic coefficient of friction is? Here's where we have to start thinking about what is actually happening. They are at rest. So what's holding them back from going down the hill? Friction. Friction is opposing their motion. They're at rest, so it's going to be static friction. We want to figure out, there's going to be some force, and I'll draw it in later. There's going to be some force that's pulling them down the hill. We want to figure out what this force needs to be in order to overcome the maximum static friction. So that's what we're really looking for. What is the maximum static friction that can exist between this ski and the snow without slipping? As soon as that force that's pulling you down the hill is greater than that maximum static friction, you know you're going to start moving. If this is less than the maximum static friction, you're not going to move. So the whole point is to figure out what the maximum static friction is. So that's what we're going to look for in our reference table. Before we do that, I guess we could do that. And then I want to draw in the rest of the forces on the diagram. So wax ski on snow. We're not looking for the kinetic in this case. We want to know what the static coefficient of friction is, 0.14, because we want to know what the maximum static friction is that can exist between these two surfaces. So let's draw in the weight, right? FG points straight down. I'm going to draw it even bigger because we're going to have to break this up into components. FG acts straight down, and the normal force acts perpendicular to the surface. That's the definition of the normal force. It acts perpendicular to the surface. Not always, oh, there's the normal force, that's opposite the weight. Nope. The definition of the normal force is that it's the force acting perpendicular to the surface. And that's what it is. So now we have three vectors going in all crazy directions. And let me see what we got here. Let me try to do this. Hold on. Okay, normally we have our x-axis like this and our y-axis like this. And most of the time that works out for us. As you can see, we have the force due to gravity acting right along with the y-axis. No extra work necessary for that. But the normal force is at this weird angle. So we'd have to find the x and y components of the normal force. The frictional force is at a weird angle. We'd have to find the x and y components of the frictional force. And that's a whole lot of work. We could actually make our lives a little bit easier by making our lives a little bit harder. So what we do is, instead of the x-axis being horizontal, we tilt the x-axis. Now we make the frictional force go in the direction of the x-axis by making the x-axis parallel to the surface. And if the x-axis is parallel to the surface, that means that the y-axis must be perpendicular to the surface. And as you could see, even though it's not a very well drawn diagram because it's not exactly 90 degrees the way I drew it, but the frictional force by definition always acts parallel to the surface, and the normal force by definition is always perpendicular to the surface. So these two will always be at 90 degrees to each other. All right? This one and this one are always at 90 degrees. So why does that help us? Now all we need to do is break one force into, we could call it x and y components, but instead what we call it is parallel and perpendicular components. Parallel to the hill and perpendicular to the hill. So here's how you do that. See where your normal force is right here? You're going to continue that line as a dotted line. And how do you know where? Some people try to draw it forever, or down to the bottom of this hill where we drew the 30-degree mark. You can't do that. It's limited because now that's not right. That's not what we want to do. You want to just draw it just enough so that when you draw the parallel component, the one parallel to the hill, it cuts it off right there. This line has to be parallel to this line. So this line can only go until it reaches this line. It's like a way to draw your vector diagram. This is 90 degrees. And now we have a right triangle, even though it's not a very good diagram. But you could see we have a leg, and this is the hypotenuse right here. That's 90 degrees. So we need to know the angle. This angle is always equal to this angle here. So if you know this, you know that is 30 degrees. Now we need to label these things. So this is the weight, Fg. That's definitely the weight. Part of the weight acts perpendicular to the hill. So that's this line here. And part of the weight acts parallel to the hill. That's the thing causing the skier, you can see it looks like little skis. It causes the skier to go down the hill. This is the force that's trying to overcome the frictional force. You could draw it up there if you'd like. I don't like to draw the forces twice on my diagram, and it's more convenient to have it down here because we're about to do some trig, so we have a nice triangle like that. Okay, everybody on board? That was the toughest part. Like right now, the way I drew this diagram, you should be able to figure out everything else. Drawing the diagram is the hardest thing. All right, so now it says, does the skier remain at rest or slide down the hill? What we want to know is FSS max. In order to do that, we want to try to do, I guess we could write it out of order here. So FFS max is equal to mu S Fn. Now there's a couple things we have to do first. We could figure out, okay, the coefficient is 0.14, but what the heck is the normal force? That's going to be a big part of getting to this final answer. We'll make sure we have room to write it in, because there's going to be a lot of steps in between now and then. So we're looking for the normal force. the normal force is being exactly balanced out by the perpendicular component of the weight. So let's see. We have Fg is equal to mg. Fg is equal to the mass times 9.8. So the weight is 735 newtons. So you can write that in, 735 newtons. Now that is not equal to the normal force. This and this are not going in the same direction. We want to find the component of the weight that acts perpendicular to the hill. So to do that, we have to figure out, here's the vector that we want. Okay, and here's our right triangle. All right, is this opposite, adjacent, or hypotenuse? It's adjacent to this angle. So we have the adjacent, or we're looking for the adjacent, and what do we have? We have Fg. Is that opposite, adjacent, or hypotenuse? That's the hypotenuse. So we have adjacent and hypotenuse. Are we going to use sine, cosine, or tangent? Adjacent and hypotenuse. We're going to use cosine theta is equal to the adjacent, Fg perpendicular, over the hypotenuse, Fg. And when you solve, you get Fg cosine theta, which is kind of like the shortcut. Fg perpendicular is always equal to Fg cosine theta on these hill problems, inclined plane problems. So it's going to be 735 cosine 30. And the perpendicular component is equal to 637, around 637 newtons. So that is Fg perpendicular, which is equal to the normal force. They're balancing each other out. The skier isn't going through the hill. The skier isn't being thrown off of the hill. The forces are balanced in the perpendicular direction. So the normal force is 637 newtons. That's good. Now we can figure out what the frictional force is. The maximum static friction that exists between these two surfaces is about 89 newtons. So that's the maximum static friction. Okay. But are we ready to answer the question? Do we know if they remain at rest or not? We just know that the maximum force that can exist between the two is 89 newtons. If Fg parallel is greater than 89 newtons, then it's going to slide. If it's less than 89 newtons, it's not going to slide. So let's figure out what Fg parallel is. I'm going to try to find a good place to write this in. Let me see. All right, so for Fg parallel, I'm just going to skip right to this step. All right, we're looking for this. Is this opposite, adjacent, or hypotenuse? It's opposite the angle. And we're also going to use the hypotenuse. I know we have this one here, but if we want to do the shortcut, we have to use the opposite and the hypotenuse. So we're going to use sine. So Fg parallel is equal to Fg sine theta. Fg parallel is equal to 735 sine 30. Fg parallel is equal to 368 newtons. That's a lot of force, 368 newtons. That's because it's the weight of the person that's acting parallel to the hill. So if you wanted, you could like redraw it up here so you could kind of see what's happening. Fg parallel equals 368 newtons. We are comparing this force to this force. Which one's bigger? That's right, Fg parallel. So they slide down the hill. It's greater than the maximum static friction. They're going to slide down the hill. Does it remain at rest or slide down the hill? Slides down hill. Fg parallel is greater than FFS max. Okay, B. If they do slide down the hill, what is their acceleration? So now, to find the acceleration, we want to do Newton's second law. we know the initial velocity and we know the distance that they're traveling, but we don't know the time or the final velocity or the acceleration. So we can't use kinematic equations. If they're asking for the acceleration, then we must be able to find it using Newton's second law. So the thing we have to know is the net force. So we're looking again at these two forces. We want to find the net force between those two. Well, hold on a second. Are we still have the same frictional force? I don't think so. Is that static friction now? It's sliding? Nope. So we're going to get here, but there's a couple steps we have to do first. First, let's figure out what is the kinetic friction. So K is equal to mu K Fn. Why do we need to know the kinetic friction? Because they're sliding. They're sliding down the hill. And I think it's 0.05. Yes, it is 0.05. So that's for kinetic. So 0.05 times the normal force, which is the same because the mass didn't change and we didn't change our angle of the hill and we didn't change what planet we're on. So the normal force is still the same. No extra work from that perspective. We just have a new frictional force because they're sliding. So you get 32 newtons. Listen, if it makes it easier, you could redraw it quickly and only draw in, we have FG parallel and we have FK, the kinetic friction. You also have Fn and FG perpendicular. But when we find the net force, it's just between these two forces here. The frictional force is only 32, and FG parallel is 368. So let's find out what that net force is. I'm going to erase this, though. Okay, so to find the net force, we want to just look at the definition of the net force. It's the sum of all the forces. So FFK plus FG parallel. This is K now, just like we had in our previous diagram. Okay. So the net force is equal to 32 newtons plus 368 newtons, but they're not going in the same direction. They're not both positive. The frictional force is acting up the hill. We kind of drew that pointing to the left. So to show that they're going in opposite directions, we say, okay, up the hill is negative. Down the hill, we'll call it positive. So the net force is equal to 336 newtons. So that's the force that's causing you to go down the hill when you add them all together. So that's the net force. Let me draw a little line here, something like this. So the acceleration is equal to the net force divided by the mass. The acceleration is equal to 336 divided by 75. So that's equal to about 4.5 meters per second squared. So what does that mean exactly? Remember what acceleration is. You're getting 4.5 meters per second faster every second. So at the end of 1 second, they start from rest, you're going 4.5 meters per second. At the end of 2 seconds, you're going 4.5 faster than that, so you're going 9 meters per second. Don't forget what acceleration actually is. So the part 2, what is their final velocity after they've traveled the 20 meters to the bottom of the hill? Let's write down what we have. The initial velocity is 0 meters per second. The acceleration we just calculated, 4.5 meters per second squared. They tell you the hill is 20 meters long, and they're looking for VF. We don't care what the time is. So you look in your reference table for an equation without time. It's not this one. This has time, this has time, this has time, this has time. Here we go. VF squared equals VI squared plus 2AD. We're looking for VF. VI is 0. 2 times 4.5 times 20. So VF is equal to, we could do VF squared is equal to 180. You take the square root of both sides, and VF is about 13 meters per second. Then it says how long does it take them to reach the bottom of the hill. So now we are looking for T, and you have everything else. So you could take your pick on which equation you want to use. My go-to is normally this. VF is 13, VI is 0, 4.5 T. So you do 13 divided by 4.5, and you get about 3 seconds if you rounded. What force should be added to bring the skier into equilibrium? Very good question. Now you have to look at your diagram again. What's going to cause this guy to become in equilibrium? Let's look at the, I'll redraw it again. So here we got this FG parallel is equal to, that was 368 newtons, the frictional force, and let's assume that it's kinetic. Now we're sliding. We said it was 32 newtons. So what force should be added to bring it into equilibrium? That means that the net force would be 0 newtons. That means that the forces were balanced. So what direction do you think we should exert this force? If we drew this to scale, this would look something more like this. So to make it balanced, we'd have to add another force going in that direction. We'll call that the applied force. Sorry for the hastily drawn free body diagram there, but that's the idea, right? That's what we want to get to. So let's use the net force equation to figure out what that should be. So the net force is equal to the sum of all the forces. The frictional force plus FG parallel, the component of the weight that's pulling you down the hill. And now we want to add an applied force to bring it into equilibrium. And again, since it's in equilibrium, the net force is 0 newtons. The frictional force is 32 newtons. We'll make it negative because that's what we did before. FG parallel is 368 newtons. And the applied force is what we're looking for. So now you get 0 is equal to 336 plus FA. You subtract 336. So the applied force, you get a negative number, which is what we expected. It's in the same direction as the frictional force. So you get 336 newtons. If you wanted, you could say 336 newtons up the hill in the same direction as the frictional force. Okay. If they don't slide down the hill, what is the minimum angle that would make them slide down the hill? Not applicable. We already did it. So boom, that's good for the first one. This is already 23 minutes long, so I'm going to make a part 2. Have a good day.